Now, this is a rather different view though, because one of the things I insisted right in the beginning is that current flow only depends on the electrons in this energy window. Things down here don't really matter. On the other hand, this approach tells you that current flow depends on the total number of electrons. And that looks like a very different thing. And what I'll try to show you is that that approach actually is equivalent to this if you only have states described by a single energy momentum relationship. On the other hand, there are all kinds of situations where this one won't work very well. You'll have problems with this. But what we have obtained already, namely the expression that we started with, this Q square diffusion coefficient times this density of states, that expression is much more general. This holds in general, whereas this Drude formula is a specialized thing which is sometimes equivalent but cannot really be used in general. But usually people remember the Drude formula. That's what they usually think in terms of. And the reason is something like this, that in the normal approach, you see, the Drude formula is relatively easy to obtain. In fact, I'll explain to you in a minute how we get that. And so, if you take a standard solid-state physics text, that will usually be in, like I say, chapter 1. Whereas this would come much, much later after you have gone through advanced formalisms. But what our bottom-up approach, where we started from this idea of an elastic resistor, allowed us to do was, we obtained this result in a relatively elementary way. And the point I want to make is, this is really much more general. This is the one you can count on in general, is more generally applicable, whereas the other one is relatively specialized, sometimes works, but you can get into trouble even if you just try to apply it to graphene, for example. Because with graphene, as we discussed, the energy-momentum relationship is linear. It doesn't look like what I've drawn here. It looks like E equals V0P. So it's linear with momentum. And in that case, it's not obvious what mass to use even here, for example. On the other hand, if you're using the other relationship, there is no problem, because regardless of what the energy-momentum relationship is, you can always calculate the density of states like we discussed. There's a well-defined diffusion coefficient, and there's really no problem. Whereas here, you immediately get into questions about what mass, for example. And we'll see what actually one should use. That's kind of what we'll be talking about in this module and the next one. Okay. Let me just quickly outline how people obtain this result. And the argument, let's just do it in 1D for simplicity. That usually the argument goes that electrons are driven by electric fields, and so the force that an electron feels is QE, and according to Newton's laws, QE should be equal to m dv dt. And of course, if this were everything, then when you apply an electric field, the electron should be continually accelerating, but instead it reaches a steady state, because when electrons are going through a solid, it's like going through a very viscous medium, where there is a very strong viscous drag, which you model as mv over tau. So this is what you call the mean free time. That's the momentum, and the more the momentum that is lost due to this viscous drag. I'm not going through this too carefully, because my whole purpose is just to give you an idea of how this argument goes, and I'm not going to make use of any of this. The only reason we are going through this is the standard thing that you'll see in freshman physics. This is the result that's most widely known, and since our result looks a little different, I feel it's useful to try to connect the two. So, and just want to remind you, if you have seen this before, how this one is obtained. So then you say that at steady state, we can drop this, and that tells you that the momentum, the steady state momentum that electrons will achieve, will be given by QE tau. I can take the m here. And then the argument goes that the current depends on, is given by Q, N, V. I guess if we are doing this in one dimension, it's the number of electrons per unit length times V. And this you can argue, again from elementary considerations, that if you have a certain number of electrons per unit length, all traveling with a certain velocity, then the rate at which electrons will cross you per second will be number of electrons per unit length times velocity. This is it's a fairly simple argument based on the idea that, if you had a bunch of electrons traveling with some velocity, then if I stand here and watch how many cross me, what I can show is the number that will cross me per second will be the number of electrons per unit length times that. And now if I multiply by the charge on an electron, I'll get the current. So this then leads to Q square, Q n over L times V, so it's Q square over M tau and this N times V, etc. And this is then what leads to this expression for conductivity that I mentioned before. This is what you'll see in freshman physics texts. Now, what is problematic about this is, it's a very simple derivation, which is why you see it everywhere. The problematic about it is it raises all kinds of questions. So, for example, if indeed electrons move due to an electric field, then what about all the other states down here? Because, as I mentioned, usually in a solid, you don't just have one little energy band here. You have all kinds of energy levels available at different energies way down here also. And what this energy momentum relation that we talk about, that's something that just applies to this narrow energy range. That's where you can use that. Down here, you cannot really use, there's all kinds of states down here, which we are not accounting for. But if electrons move due to electric fields, then you'd think that all these electrons should be moving. Why just these? Well, that's where you say that, some electrons are free and some aren't. So these are the free electrons. And so you see, you kind of have all kinds of mysterious issues coming up. Why are some electrons free? Why aren't these things conducting, etc.? On the other hand, the viewpoint that we adopted here, that gives a very natural explanation for this. And that is what we did in week 1. Namely, only those electrons conduct which are in this energy range between mu1 and mu2. Why? Because those are the states that one contact wants to fill up, another contact wants to empty. Down here, both contacts want to keep them filled, which is why they stay filled, nothing happens. You see? So it follows very logically, there's really no problems there. Whereas this picture, you see, it's simple, but it raises all kinds of issues if you think too deeply. Okay. Now, what I want to show then is, quickly, is how our expression here will actually get you this expression also if you ignore all these other bands and just work with one band like this, given some energy momentum relation. And what we do here is, we make use of this relation that we obtained in module 2.1. This dVp equals nd. So let me write that up here, and you'll see. So the expression I want to make use of is that the density of states times Vp is equal to n times d. So what you can see is, the expression for conductivity I have there, I could write in the following way, Q square, and then there's the diffusion coefficient, which is V square tau, divided by d, the number of dimensions. As you have seen, one dimension it's 1, 2 dimensions it's half, 3 dimensions is 1 over 3, that V square tau over d. And then there's the density of states, and then like 1 over L or 1 over WL or 1 over AL, depending on whether we have a 1D conductor, 2D conductor, or a 3D conductor. Okay. So next step is, instead of dV, let me replace from this expression. So what you would get then is Q square dV divided by the number of dimensions is equal to N divided by P. So what you'd have is something like this. V, maybe I'll write tau first, V, and then dV divided by D. And what I'm saying is we could replace that quantity, dV divided by the number of dimensions, with N divided by P. So I could write here N divided by P. So now if you compare to the root formula from here, so let me just write that here for comparison. So the root formula is Q square tau over M times N times 1 over L, 1 over WL, 1 over. So you'll see those look basically the same equation. You see, looks very similar, and the two would be equivalent if we identify mass as momentum divided by velocity. Now, which of course looks, well, you might say, well, P equals mv, we know that. You know, momentum is mass times velocity. Yes, but that again is, when you have a parabolic relation like E equals P square over 2m. Let me. So when you have E equals P squared divided by 2m, then velocity is in general dE dP, and that's equal to P over m. And so this looks fine. This is the one that we're used to. On the other hand, if you are talking of, say, graphene, where E is equal to V0P, then you'll notice actually velocity is constant. Is dE dP is just a constant number V0. It's independent of momentum. So what that means is that if I looked at the mass, it would be P over V. The V is a constant, and so the more the momentum, bigger the mass. So it is almost as if electrons here with less momentum have a small mass, and electrons, when they go up there, they have a much bigger mass. You see? And this leads to unusual properties when you try to look at the conductivity. And that is kind of what we will talk about in the next module a little more. That the consequences of this, of not having a parabolic relation, that is, this E equal being proportional to P squared, that's what you normally call a parabolic relation. In the sense, this is like, if you had plotted it, it would look like a parabola. But if you don't have a parabolic relation, like a linear relation or anything else, then you see the mass can be not a constant, but something that depends on energy. And in that case, you have to interpret conductivity that you measure much more carefully, taking into account the fact that the mass itself is energy dependent. Anyway, so this is what I'll talk about in the next module.